So Ramil, you've got Ryan Sanders first, haven't you? You've got his recorded
Yeah,
talk ready?
I've got his talk up and ready.
Great.
Seemed like it was working, so hopefully we'll sort this out.
We're live now and I'll start recording.
Well, what should I do about questions, I guess, for Ryan?
I guess we're not going to have any for
Yeah,
his.
we just put him in the Slack and Ryan can answer them later, I guess.
Exactly. I don't think we ever agreed with Ryan what we were going to do, but if people do have questions, then yeah, hopefully we can drag him on later.
Check in.
Yeah. I mean, we'll keep the Slack workspace open for at least a couple of weeks afterwards, if not indefinitely.
Right. All right. So should we start? Or?
Yeah, we may as well. We've got a flood of people coming back in now.
All right. All right, everyone. I think we can get started on the second session of the day here. We have a very nice lineup of talks. The first one is by Ryan Sanders, but he is actually pre-recorded it because he couldn't make this time live. So I'm going to try to play this. And if you have any questions for Ryan afterwards, just put them in the Slack and hopefully we'll get Ryan to check in and answer them later. So put them again underneath the talk, underneath Ryan's talk in the Slack under session 2B. Similarly with the questions for other people, just write them into the Slack and we will, I'll read them out at the end, as many as I can get through. Okay, so with no further ado, I will try to share my screen and play Ryan's video here. Okay, so let us go to full screen. And here is Ryan Sanders from UC Davis.
A postdoc at UC Davis. I'd first like to thank the organizers of Sazerac for allowing me to pre-record this talk since I couldn't make the time live. Today I'd like to talk to you about the metallicities and ionization properties of galaxies in the epoch of reionization, and in particular what we can learn from extreme galaxies at redshift 2 that are analogues of galaxies at redshift greater than 6, and future prospects for measuring metallicity with synergies between James Webb and ALMA. This work has been done in collaboration with the MOSDEF survey team shown on the left, and in particular with Alice Shapley at UCLA, and also with the group of collaborators that I've listed in the lower right of this slide, in particular with Tucker Jones at UC Davis. The James Webb Space Telescope will soon provide us with rest optical spectra of galaxies at redshift greater than 6 for the first time. And a big question is, what will we do with the measurements made from these first James Webb spectra? From the NIRSPEC, NIRCam, GRISM, and NIRIS instruments, James Webb will measure the H-alpha and nitrogen 2 emission lines to redshift 6.6, oxygen 3 and H-beta to redshift 9, and oxygen 2 and neon 3 to redshift 12. Some major science objectives for measurements of these emission lines include characterizing the chemical abundances and chemical evolution of galaxies at the highest redshift, the ionization state of star-forming regions, and the properties of massive stars in these early galaxies. And in particular, the last one has connections to the ability of star-forming galaxies to reionize the universe. The tools that we'll use to extract this information from measurements of the emission lines include strong line metallicity calibrations that convert line ratios into gas phase metallicities, and modeling of the emission line spectra using photoionization codes. Now, even at redshift of 1 to 2, the ionized gas conditions in H2 regions are different than they are in the local universe, requiring different metallicity calibrations and a different set of assumptions for modeling redshift 2 emission line spectra. And we expect that the situation is possibly even more different for typical galaxies at redshift of 6. Therefore, in order to maximize the science return on the first wave of James Webb observations, we need to answer two questions. The first is, what metallicity calibrations are appropriate for use at redshift greater than 6? And the second is, what is the proper set of assumptions for photonization modeling of emission spectra from redshift greater than 6 galaxies? I'm going to address these questions using a sample of about 20 galaxies of redshift 2 with direct method gas phase metallicities. These direct method metallicities are very robust and are derived from the electron temperature based on detections of weak auroral emission lines such as oxygen 4363 in the REST optical and oxygen 31663 doublet in the REST UV. I've shown some examples of detections of these weak emission lines for galaxies of redshift 2 on this slide. Now, why this sample at redshift 2 should be able to inform our knowledge of galaxies of redshift greater than 6. Here I've shown on the left specific star formation rate and on the right equivalent width of O3 plus H beta, both as a function of stellar mass. The redshift 2 direct method sample shown in red here has much higher specific star formation rates and emission line equivalent widths on average than typical redshift 2 galaxies shown in blue on these slides, and much higher of course than redshift 0, which is shown in the gray. And in particular, if I put up on these slides some determinations of specific star formation rate and H beta plus O3 equivalent width at redshift 7 based on broadband photometry, we see that this direct method sample at redshift 2 is actually comprised of very good analogues of UV bright galaxies in the epoch of reionization. Let's first take a look at the metallicity calibrations. In these plots, I'm showing on the left the R2-3 line ratio and on the right the O3-2 line ratio as a function of direct method metallicity. The redshift 2 auroral line direct method sample is shown in red, and the median of this extreme redshift 2 sample is shown in the black diamond. Now I'm comparing to some other samples here. In the black line we have redshift 0 H2 regions, in pink we have typical redshift 0 galaxies, and in green line we show local analogs of high redshift galaxies. This is from work from Beyond et al. 2018, these high redshift analog calibrations. And what we find is that typical redshift 0 galaxies and local redshift 0 H2 regions do not produce calibrations that can reproduce the metallicities of the extreme redshift 2 sample. But local analogs of high redshift galaxies, again shown in the green line, appears to reproduce the average properties of the extreme redshift 2 sample quite well. And so the conclusion here is that local analogs of high redshift galaxies can produce accurate metallicity calibrations that can be used for galaxies at redshift of greater than 6. We should not use typical redshift 0 metallicity calibrations. A caveat here is that we haven't confirmed this for nitrogen-based indicators, only for indicators that are ratios of oxygen, neon, and hydrogen lines. We performed photoionization modeling of the extreme redshift 2 sample to place constraints on the ionization parameter and the shape of the ionizing spectrum. Here the shape of the ionizing spectrum is parameterized in the stellar metallicity, which traces the iron abundance. And in particular, because we have the direct method metallicities, we can fix the nebular metallicity in the photoionization models, allowing us to get non-degenerate solutions for ionization parameter and the shape of the ionizing spectrum. The results are shown here. In the left panel, we show ionization parameter versus nebular metallicity. And what we find is that the extreme Z of 2 sample is not offset from the local relation between ionization parameter and nebular metallicity. On the right, we show stellar metallicity, which again traces iron abundance, versus nebular metallicity, which traces the oxygen abundance. And what we find is that the stellar metallicity is lower on average than the nebular metallicity. And this indicates that these galaxies have supersolar oxygen to iron abundance ratios, which drives hard ionizing spectra because iron poor stars are hotter and thus produce harder spectra. Now, this supersolar oxygen to iron abundance ratio is expected for galaxies that have rapid formation timescales and high specific star formation rates because oxygen comes from type 2 core collapse supernovae and is thus produced on a short time scale of approximately 10 megayears, while iron comes predominantly from type 1a supernovae, which are delayed, and the enrichment of iron happens on a timescale of approximately a gigayear. So our suggestions for modeling redshift greater than 6 emission spectra are to assume the local relation between ionization parameter and nebular metallicity, while assuming that the stellar metallicity, that is the iron abundance, is approximately 1/5 the value of the nebular metallicity, which traces the oxygen abundance. This value of 1/5 is approximately the limit for pure type 2 supernovae enrichment. Now, it's very useful to draw conclusions from these analogues of galaxies in the epoch of reionization, but ultimately we'd like to test these inferences by measuring direct method metallicities of galaxies at the highest redshifts. But the truth is that even with James Webb, it's not going to be feasible to detect oxygen 34363 for galaxies of redshift greater than 6. Even at low metallicities and high electron temperatures, this line is still about 50 times fainter than oxygen 3 5007. And so we need an alternative and more accessible method to derive the electron temperature in the epoch of reionization. To this end, we've developed a new method to measure direct method metallicities using measurements of the oxygen 3 infrared lines at 52 microns and 88 microns from ALMA in combination with rest optical lines from JWST. This method is very similar to the traditional method that uses oxygen 4363 to get the electron temperature, but in this case the electron temperature is derived from oxygen 352 microns or 88 microns. And for these UV bright redshift of 7 sources, you could get the ALMA line, the infrared lines with ALMA in approximately 10 hours per target, and the optical lines with James Webb in a few hours per target. Now, we don't have rest optical emission line measurements for galaxies at redshift greater than 6 at the present time, of course, since we don't yet have James Webb. So what we've done is instead inferred the H beta luminosity from the UV star formation rate for galaxies of redshift 8. We have assumed fiducial values for the electron temperature and the electron density, as well as the ionization correction factor. All of these assumptions equate to approximately a 0.4 dex systematic uncertainty in over H, but basically what you see in this equation at the bottom of the slide is that we can determine the oxygen abundance from a combination of the 88 micron oxygen 3 line that's been measured by ALMA for several redshift 8 sources and the UV star formation rate. I'll say very briefly that we have tested this 88 micron method under our set of fiducial assumptions on a sample of redshift 0 low metallicity dwarf galaxies and find that it recovers the metallicities inferred from the traditional method using oxygen 3 4363 quite nicely with a nice 1-to-1 relation. The 1 sigma scatter is 0.2 dex. Here I'm showing the results of applying this new method to a sample of 5 redshift 8 galaxies with measurements of the O3 88 micron line from ALMA. For these UV bright galaxies of redshift 8, we find a typical metallicity of about 10 to 20% solar at 10 to the 9 solar masses. This represents an evolution of 0.5 to 0.9 dex lower in metallicity at fixed stellar mass compared to the redshift 0 mass metallicity relation. And this is a similar typical metallicity to the redshift 2 extreme sample that I was using earlier as analogues. These metallicities are low but not extremely low, which carries important implications about the star formation histories of these galaxies. The future prospects of using synergy between ALMA and James Webb to study chemical evolution at redshift greater than 6 are very exciting. To conclude, I'll go ahead and put up a summary slide that encapsulates some of the main points of the talk. I apologize I won't be able to answer questions live during the conference, but I put my email address in the upper right corner of this slide, and I'd be happy to discuss via email if anyone has any questions. Thanks for listening.
Right. So yes, so well, thank you, Ryan, in absentia. As I said, if you have any questions for Ryan, please feel free to put them into the Slack chat for his talk. Otherwise, we will move on to our next speaker, who is Ramesh Mainali. who's going to tell us about gravitationally lensed Z of 2 reionization-era analogues and implications for carbon-3 detections at Z greater than 6. So Ramesh, you can go ahead and start sharing your screen. And
okay, can you hear me?
Yes, go ahead.
Okay, great, thanks. Okay, hello everyone. I'm Ramesh Mainali, currently a postdoc at NASA Goddard Center. First of all, I would like to thank the organizing committee for providing me this opportunity to talk about my research. Today, I'm going to talk about some of my recent work on the study of gravitational-lensed reionization-era galaxies. This work has recently been published and available on arXiv. Now, to begin with, here I show a few spectra of reionization-era galaxies showing detection of strong carbon-3 emission at redshift greater than 6. Since past few years, we have been finding these exciting carbon-3 features among redshift greater than 6 galaxies, which has never been found in star-forming galaxies at lower redshifts. Understanding these features is particularly important in context of ordy galaxies and their role in reionization. While the present sample is still small, we find that about 14% of redshift greater than 7 galaxies show intense carbon-3 with equivalent width greater than 20 angstrom. So how does this compare to lower redshift sample? Well, in a survey of 184 star-forming galaxies targeted at redshift of around 1, none were found with carbon-3 above equivalent width of 20 angstrom. This suggests that intense carbon-3 is more common at redshift greater than 6 than at lower redshifts. Now, in order to understand the carbon-3 emissions we are finding at redshift greater than 6, it is important to explain origins of these lines, which is currently unclear. We currently don't know whether massive hot stars are powering these lines or AGN are required to explain these features. Now, in part, this problem arises because some photoionization models struggle to produce these intense carbon-3 emission with equivalent width reaching above 20 angstrom using only hot stars model. And the only way we get above 20 angstrom carbon-3 emission is using AGN models. If this is the case, it would imply that the population of carbon-3 emitters we are finding at redshift greater than 7 are actually AGN population. Currently, it is extremely difficult to tackle this issue at redshift greater than 6. However, it might help if we can find similar sources at a lower redshift where more detailed study is possible. In the literature, we find that that equivalent width greater than 20 angstrom carbon-3 detections are mostly associated with AGNs. Among star-forming galaxies, we find that carbon-3 equivalent width increases with oxygen-3 equivalent width, as shown in figure. However, current survey have yet to find sources with carbon-3 equivalent width as strong as those observed at redshift greater than 6. In part, this may be because very few objects with oxygen-3 and s-beta equivalent width reaching around 2000 angstrom have been targeted in surveys. Now, in order to answer some of these questions, we recently initiated a spectroscopic campaign aimed at targeting extreme emission line galaxies at redshift of around 2 in Hubble clusters, especially from a program called RELIX, where we looked for carbon-3 emission among sources with oxygen-3 plus and s-beta equivalent width reaching as large as 2000 angstrom. Now, by targeting gravitational-lensed galaxies, we are basically selecting dwarf systems that likely have lower gas and stellar metallicity, both of which may enhance production of carbon-3 line. By selecting photometric axis objects with oxygen-3 and s-beta equivalent with reaching up to 2000 angstrom, we are selecting systems likely dominated by hot younger stars that appear after a burst of recent star formation. So the question is, do these systems tend to show more intense carbon-free emission? So here are the spectra of the objects from our sample showing detection of strong carbon-free line. In some of these sources, we find carbon-free equivalent with as large as those detected at redshift greater than 6, reaching beyond 20 angstrom. At this redshift, combined optical and UV spectroscopy provides insight into physical conditions of these systems. Okay. So first thing we can look into is the source of intense carbon-free with equivalent with beyond 20 angstrom. Using emission line research and with the help of diagram like classic BPT diagram as shown in figure, we infer that these systems are most likely low metallicity galaxies dominated by young stellar population. We find no other evidence of Asian activity in this system, yet we are seeing carbon-free equivalent with reaching beyond 20 angstrom. We further use line ratio diagnostics like commonly used O32 and R23 to compare this system with star-forming galaxies at redshift of 0 and redshift of 2. Our analysis suggests that the system is dominated by highly ionized gas as proved by its large O32 value. And using metallicity sensitive lines, we measure metallicity of around 8% solar metallicity. Now, one may argue that these systems may have enhanced carbon abundance and thus show stronger carbon-free line. However, we measure subsolar carbon to oxygen abundance of about 40% solar value as expected for similarly metal poor systems. We have further used a photoionization tool called Beagle to model broadband LCD and available emission lines. The modeling further supports that the observed data are better reproduced by young stellar populations of around 3 million years age and require very large ionization parameter and low gas phase metallicity of around 10% solar, which is expected from a dwarf galaxy population that are caught in the midst of large bursts of star formation. Now coming back to this carbon-free versus oxygen-free equivalent with relation, we can now see that strong carbon-free equivalent with reaching beyond 20 angstrom as seen at redshift greater than 6 require very strong oxygen-free and S beta with equivalent with similar to 2000 angstrom. Recent studies have shown that these strong oxygen-free emitters become more common at redshift 7, representing around 20% of the population with largest specific star formation rate undergoing recent burst of star formation. Now there is some scatter in this relation, and if you want to learn more about this scatter and the origin of this scatter, please listen to Mengtao's talk right after this talk. Now putting together all these evidences, this suggests that strong carbon-free emission that we are finding at redshift greater than 6 likely reflect evolution of galaxy population from reionization epoch to redshift of around 2. In the reionization epoch, larger fraction of galaxy population likely show larger specific star formation rate and hence strong optical line equivalent with following extreme bursts of star formation. At the same time, earlier galaxies are likely to have lower metallicity compared to lower redshift population. Okay, in summary, I present detection of strong carbon-free emission similar to reionization-era galaxies among gravitational lens extreme emission line galaxies at redshift of around 2. Our combined analysis using optical and UV lines suggest very low metallicity hot stars are likely powering strong carbon-free lines. This is further supported by our photoionization modeling that reveal young star population of around 3 million year age, high ionization parameter, and low metallicity. Finally, detection of strong carbon-free emitters in the reionization era may reflect population of galaxy with lower metallicity dominated by young stars undergoing recent bursts of star formation. Thank you.
Thank you very much, Ramesh. That was very, very nice. Yes, so let's look at some questions. Do we have any questions for Ramesh? So there's one from Rebecca, Rebecca Bowler. She asks, is there any contribution from AGN, or can the spectra be completely described by star formation?
With our current data, our data is better described by star formation rather than AGN. As I saw in some of this BPT diagram, we can rule out some of AGN contribution using this BPT diagram and also we don't see any any evidence of other AGN like spectral features in our data, and also these our emission lines are very narrow compared to what we expect from AGN spectra.
Tom Toons asks, how do you understand the very young ages of these stars? That is, why are there no slightly older stars with ages 10 to 30 million years, say?
That's a very good question. So basically, with our model, what we are concerning is the recent, star formation or stellar age in recent times. Okay, and we cannot actually rule out contribution of or presence of evolved star in these systems. In fact, if we model our current data with like two component stellar ages older stellar population on top of recent burst of stellar stars, then we can see that evolved stellar population as well as like around 70 or 80 years cannot be like ruled out with our current data.
Okay. Are there any other questions? There's Danielle Scherer mentions, I think this is just a comment more than a question. As a complement to your slides, the BUDS survey has studied large samples of carbon-3 emitters and finds indeed that they're quite rare. Let's see. There's a question from Hakim Atek. How does the carbon-3 versus O3 to O2 relation look like? So O3 over O2 versus carbon-3.
Yeah, so carbon-3 equivalent with tends to increase with oxygen-3 by oxygen-2, O3 to value. Actually, I didn't show that relation in here, but yeah, I mean there is like we find like it is most likely that O3 increases with carbon-3 equivalent with, and in other sense we can also see that there is a direct relation between correlation between carbon-3 equivalent weight versus oxygen-3 equivalent weight, right? And then we also find this strong oxygen-3 emitters with largest equivalent with values. They are tends to they are directly related with O3 values. So yeah, I mean there's like direct relation between carbon-3 equivalent with and O3.
Okay. Well, thank you, Ramesh. That was very, very interesting, and I think we'll move on now to Mengtao Tang. So Mengtao, can you share your screen? And start when you're ready. You will tell us about the REST UV spectroscopy of reionization analogues at redshift 1 to 3 and implications for early star-forming galaxies.
Okay, so thanks for the organizer to give me this opportunity to talk. My name is Mengtao Tang from University of Arizona. So today I'm going to talk about our new results from the Rest-frame UV spectra of reionization-era analogues at redshift 1 to 3. So in the last few years, we have obtained our first view of the spectral properties of galaxies in the reionization era. So we learned from the Spitzer data is that the optical line emission in galaxies at redshift larger than 6 is incredibly intense. Upward to 20% of this population has O3 plus H beta equivalent with larger than 1,000 angstrom. So this means these galaxies are in the midst of the burst of star formation. So this kind of extreme emission-like galaxies is very rare at redshift 2, but seems pretty common at redshift 7. So what do we know about their physical nature? So currently, we learned two things from their spectra, which seems quite surprising. So the first one, as we heard from the last talk given by Ramesh, is that the carbon-3 emission in these extreme bursts of galaxies in redshift larger than 6 are often detected with the equivalent width about 20 angstrom. So this value is much, much larger than the typical value at a lower redshift. So currently, we can hardly find such strong carbon-3 emission at a lower redshift, which makes it very difficult for us to interpret the what this line emission tells about this extreme population. So the second result is from the lemma alpha emission in galaxies in the reionization era. So we know that lemma alpha emission is very rare in the general population of redshift 7 to 8, as you can see from this plot showing the lemma alpha fraction. This is expected as the AGM is scattering the lemma alpha. However, if we look at the subset of population of massive galaxies with very large O3 plus H beta equivalent width, we see that the strong lemma alpha emission is quite common in this population. So why this lemma alpha is so strong in this population at redshift 7 is still unclear. There are two possible explanations for this. So first is that this kind of massive galaxies may sit in the larger ionized bubbles that with the accelerated reionization. And the second explanation is that these kind of extreme optical line emitting galaxies have more intense radiation field than the general population at redshift 7, which boosts both the production and the escape of the lemma alpha photons. But without a better understanding of the galaxies with extremely large O3 plus H beta equivalent width, it's hard for us to answer these questions. So one way to address this uncertainty is at a very high redshift is to take a spectra of galaxies with similarly large optical line equivalent width at redshift 1 to 3, where we can study them in greater detail. So motivated by this, we selected galaxies with very large O3 plus H beta equivalent width from a few hundred to 1,000 angstrom at redshift 1 to 3, which the values are comparable to what we're seeing at a redshift larger than 6. So previously, we have a large near-infrared spectroscopy survey targeting the rest-frame optical emission line for this population. So this is the second step of our survey. We use the optical instrument to target the rest-frame UV lines for this population. So we obtained the rest UV spectra for 100 galaxies at redshift 1 to 3 with large optical line equivalent width, including 68 of them with O3 plus H beta equivalent width larger than 1,000 angstrom. So our goal is to explore the carbon-3 and the lemma alpha property in this population, and we will use our analogues as a baseline to understanding the results we see in the redshift larger than 6 and 7. So first, I show the carbon-3 emission results. From the last talk given by Ramesh, we heard that the carbon-3 emission reaches about 20 angstrom in the galaxies with very large O3 plus H beta equivalent with about 2,000 angstrom. So if it is the case, it indicates that the galaxies with strong carbon-3 emission is just due to the hard radiation field from very young stellar populations. So if this is the case, do we see the same intense carbon-3 emission in our galaxies with very large optical line emitters? So here I show, I test this scenario with our sample. Here I show an example with very large O3 plus H beta equivalent with about 2,800 angstrom. So if the carbon-3 is uniformly strong in this population, we fully expect to see a carbon-3 equivalent with about 20 angstrom in this object. But surprisingly, when we measured the spectra, we found the carbon-3 equivalent with only 8.5 angstrom for this object, much below what we expected. So what's happening here? Here I'm showing another example with O3 plus H beta equivalent with about 1700 angstrom. And also, we found the carbon-3 equivalent with is about only 7 angstrom. So from these two examples, we see that there's a very different population from what we heard from Ramesh, that not all the galaxies with extremely large O3 plus H beta equivalent with have strong carbon-3 emission. This means that the hard radiation field associated with the young stellar population is not sufficient to power the carbon-3 emission, strong power emission. So why do some of these strong O3 line emitter show relatively weak carbon-3 emission? So we investigate this with our photonization models, and we found that the answer is metallicity. Metallicity also plays a very important role in regulating the carbon-3 emission. Here I show two examples with both large O3 plus H beta equivalent with. But one is a weaker carbon-3 emitter, and another is a stronger carbon-3 emitter. For the weaker carbon-3 emitter, it is more luminous and with a moderately metal poor gas with about 0.3 solar metallicity. For the strong carbon-3 emitter, it's much fainter and with more metal poor gas, about only 0.1 solar metallicity. So we see here that the carbon-3 equivalent with increases by 3 times between 0.3 solar metallicity to 0.1 solar metallicity. Even they have even they have very similarly large optical line equivalent width. So what this implies for the galaxies in the reionization era is that the strong carbon-3 emission found in redshift larger than 7 is also found in massive galaxies. Our results show that such strong carbon-3 emission also requires a very low metallicity, say 0.1 solar metallicity in these massive galaxies. So this indicates that this strong carbon-3 emission can be explained by the galaxy population shifted toward both a larger specific star formation rate, which is a larger O3 plus H beta equivalent with, as we heard from Ramesh, and also the lower metallicities, say 0.1 solar metallicity. So in the last few minutes of my talk, I'm going to talk about the Lam alpha result from the reionization analogues in my sample. So recall that the goal is to explore the Lam alpha properties in the population with a very large O3 plus H beta equivalent with to provide a baseline to understand why Lam alpha is very strong in this population in the reionization era. So here I show an example of our galaxies with a very large O3 plus H beta equivalent with, say, 2400 angstrom. And we also see a very large lemma alpha equivalent with over 100 angstrom. So this will provide a baseline to understand the how the lemma alpha emitter fraction vary with the O3 plus H beta equivalent with. So here's our results. We see that for galaxies with very large O3 plus H beta equivalent with, the strong lemma alpha emission line is more common in this population at redshift 2 to 3, where the IgM is mostly ionized. So this suggests that the strong lemma alpha emission seen in this population at redshift 7 may not only be a result as the sitting in the large ionized bubbles, which can boost the transmission of the lemma alpha through the IgM. So what drives this trend in the redshift 2 to 3? So this can be explained by looking at the radiation field in this population. So here I show how the ionizing photoprojection efficiency versus O3 equivalent width. With the galaxies with very large O3 equivalent width, they also have they are also the most efficient sources producing ionizing photons. So this also means that they are producing more ionizing photons and likely the lemma alpha photons than galaxies with the lower equivalent width. So galaxies with a very large O3 plus H beta equivalent width are likely to be more easily detected with lemma alpha. So what this implies for in the reionization era is that the galaxies with the O3 plus H beta equivalent width, and hence the radiation field, plays a very important role in regulating the Lyman alpha equivalent width. So when we compare the Lyman alpha fractions in galaxies over the cosmic time, especially to the reionization era, we must control these parameters, such as the intense radiation field. So for more information about the IgM surrounding this population in the reionization era and about the IgM attenuation for these galaxies, you can see more in Ryan Ansley's poster presentation. So here I summarize my talk. We lead a large rest-frame UV spectroscopy survey targeting galaxies with very large O3 plus H beta equivalent width at redshift 1 to 3, which can be used as an analog of reionization-era galaxies. We're targeting their carbon-3 and Lyman alpha emission. We found that the Lyman alpha, the carbon-3 equivalent width, there's a large variation even in galaxies with very large O3 plus H beta equivalent width. This suggesting that the large specific star formation rate is not sufficient to power the intense carbon-3 emission. The carbon-3 emission, about 20 angstrom, also requires a very metal-poor gas, reflecting a shift of the redshift larger than 6 galaxies toward both a large specific star formation rate and a lower metallicity. We found for galaxies with very large optical line equivalent width, the strong Lyman alpha emission become more common. And this can be explained by a larger Lyman continuum and also a Lyman alpha production rate in this population. So the oxygen-3 equivalent width and hence the radiation field plays a very important role in regulating the Lyman alpha equivalent width. So these factors must be controlled when comparing the Lyman alpha fraction over the cosmic time. So I will stop here and take any questions.
Thank you, Mengtao. We have quite a few questions, so we'll try to get through as many as we can. So Daniel Scherer asks, have you been able to measure directly the metallicity over each of your C3 emitters to confirm the low metallicities you're suggesting?
There are very few objects with the O3 1660 measurement, so we can measure the metallicity for a bunch of sources. The number is small, but they are consistent with what we inferred from the polarization model and also the metallicity variation in carbon-3 emission.
Mm-hmm. Okay, so Yurit asks, nice results on the dependence of Lyman alpha fraction on the O3 plus H beta equivalent width. How do the Lyman alpha equivalent width you measure in the extreme emitters, O3 plus H beta emitters at redshift 2 compared to the Lyman alpha equivalent widths measured at redshift 7 objects with comparable O3 plus H beta? Did you consider using the difference to infer the relative IgM attenuation? So I guess it's asking about.
Actually, another interesting result I haven't shown in this presentation is that we found the Lyman alpha fraction in the galaxies with large optical line equivalent width are similar for both at redshift 2 to 3 and redshift larger than 7. Both of them show about 50% show strong Lyman alpha emission with equivalent larger than 25 angstrom. So this may indicate that the first thing is that the Lyman alpha production is larger in these galaxies with very large optical line equivalent width. And also the similar Lyman alpha fraction we found at lower redshift and in the reionization era may indicate that these galaxies also require a large, trace a large ionized bubble, which boosts the transmission of Lyman alpha through the neutral through the IgM.
Okay, yeah. So probably have time for one more, although there are quite a few more. You'll have to go into the chat and answer there. But Charlotte Mason asks, beyond the Lyman alpha emitter fraction, have you looked at the Lyman alpha equivalent width distribution for these strong O3 emitters?
I have, let me see. I haven't looked at the Lyman alpha equivalent width distribution for the O3 line emitters, but I think the distribution should be very similar to what we see. should be similar to what we see in the redshift 7, as they show a similar fraction of strong Lyman alpha emission. So for the Lyman alpha equivalent distribution at redshift 7, you can see the poster presentation from Ryan Ansley.
Great. That's unfortunately all we have time for. There's a few more questions, but we have to move on. So thank you again, Mengtao. And we'll move on to the next talk from Keunho Kim, who will tell us about the importance of star formation in intensity in Lyman alpha escape from green P galaxies and Lyman break analogues. So Keunho, if you could share your screen. And here we go. Yeah, there you go.
Okay, do you hear me?
Yes.
Hi everyone, I'm Keunho Kim, PhD candidate graduating this summer at Arizona State University. First, I would like to thank the committee meeting members for giving me the opportunity to present our results. Today, I'm going to talk about the importance of star formation intensity in Lyman alpha escape from green P galaxies and Lyman break galaxy analogues. Okay, what are green P galaxies? They are local starburst compact dwarf galaxies with typically low metallicity and low extinction for their stellar mass. They are first discovered by SDSS Galaxy Zoo project. As inferred from their nickname, their optical color is greenish due to strong O3 emission line at their redshift. These two images show two examples of green P galaxies observed with SDSS color composite images. And as seen here, they are mostly unresolved with SDSS images and look like green P. Their UV spectroscopy properties have shown that most of green P galaxies are Lyman alpha emitting galaxies, and thus they are known as some of the best local analogues of high redshift Lyman alpha emitters. As for local Lyman break galaxy analogues, they are UV continuum selected local starburst galaxies showing similar properties with high redshift Lyman break galaxies. To this end, the motivation of this project is to investigate the spatially resolved central UV photometric properties, such as star formation intensity. In this talk, star formation intensity is the parameter is that star formation per unit area and equivalent to star formation rate surface density. And we'll investigate the possible associations with the Lyman alpha escape mechanisms, also with our measured star formation intensity. We've selected a sample of 40 green P galaxies and 15 Lyman break galaxy analogues from the literature that are all observed with HSD course spectroscopy and the associated near UV acquisition images. The near UV images have high spatial resolution in the sense that their typical point spread function is only 2 pixels, corresponding to 0.047 arcsecond. Thus, with high spatial resolution near UV images and the physical proximity of our sample local analog galaxies, we are able to measure the central 250 parsec region star formation intensity of our sample galaxies, which is only achieved for these local analogs with high HSD images. In order to do so, we accounted for redshift-dependent nonlinear effects such as PSF. And in order to account for those effects, we first performed the point spread function deconvolution against the original image. And we also removed the image noises by performing denoising procedure. And in order to only measure the uniform 250 parsec same physical region star formation intensity, we resampled pixels and then derived the Petrosian galaxy segmentation map to derive the total star formation rate from NUV images as well. this figure shows 4 different green pea examples. Each row shows an individual galaxy, and from left column to right columns, original cos and UV image, point spread function deconvolved, and denoised images. And lastly, we corrected for galactic Milky Way and internal extinction, as well as our measured UV star formation intensity is K-corrected at the wavelength of 1877 angstrom. So first of all, the measured central star formation intensity of green peas and Lyman break analogues shows the mean star formation intensity of 15 and 28 solar mass per year per kiloparsec square, respectively. And this high SFI star formation intensity is 2 to 3 orders of magnitude larger than typical star forming disk galaxies. And interestingly, all sample green peas and LBAs have large star formation intensity larger than 0.1 solar mass per year per kiloparsec square, which is a suggested SFI threshold for generating galactic scale outflows winds. As our project aims to investigate the dependence of Lyman alpha strength and escape on star formation intensity, we directly compare our measured central SFI with Lyman alpha equivalent with in the left panel and Lyman alpha escape fraction. As shown in the distribution and the associated Spearman correlation coefficients within the red circles, there are no significant positive correlations with our measured SFI and Lyman alpha properties in our sample green peas and LBAs. However, when we consider the parameter of specific star formation intensity defined as star formation intensity divided by galaxy stellar mass, we found statistically significant positive correlations, as well as the observed increasing trend between specific star formation intensity and Lyman alpha equivalent width, as well as Lyman alpha escape fraction. And the correlation coefficients are among the most significant among the ones we've investigated, such as with 1/m star or totals, just specific star formation rate, as shown here. Also, interestingly, among our sample green peas, the conformed Lyman continuum liquors show high specific star formation intensity compared to the rest of the sample galaxies. The discussion is the high central star formation intensity in green peas and LBAs, which is typically 2 to 3 orders of magnitude higher than typical star forming disk galaxies, which is satisfying the physical condition for generating galactic scale winds. And in addition to this, if we, by considering the effect of galaxy stellar mass as a proxy of gravitational potential and the associated escape velocity for gas and dust to be ejected, the parameter of specific star formation intensity as a driving parameter for Lyman alpha photon escapes can be likely related to the clearing power of ISM with holes represented by strong SFI in shallow gravitational potentials, which is likely making less chance of resonance scattering of Lyman alpha photons on their way to escape. This simple cartoon below shows how Lyman alpha photons indicated by violet arrows can escape from the central starburst region in green pea galaxies, based on our specific star formation intensity explanation. So the summary is by fully utilizing the physical proximity of local analogues, green pea galaxies and Lyman break analogues, as well as the high near UV spatial resolution images, we've measured the uniform central 250 parsec star formation intensity of these local analogs of high redshift Lyman alpha emitters and Lyman break galaxies. The measured central SFI of Greenpeace and LBAs show high SFI compared to typical star-forming these galaxies, which is well above the suggested SFI threshold of 0.1 for generating galactic scale outflows. While the central SFI alone doesn't show significant positive correlations with Lyman alpha properties of Greenpeace and LBA, we've found that the parameter of specific star formation intensity, defined as SFI per stellar mass, shows the significant positive correlations with Lyman alpha equivalence width and Lyman alpha escape fraction. And our analysis thus have suggests a Lyman alpha escape mechanism where strong galactic outflows can make significant holes in the ISM in shallow gravitational potentials through which Lyman alpha photons can ease their escape. For further details, please see our recently published paper, and also you can email me, and I'm happy to take questions. Thank you.
Thank you, Keunho. Yes, so very interesting talk. Thank you very much. And we have some questions. So Maxime asks, sorry if I have missed this during the talk, but is the SSFI, the SFR within 250 parsecs divided by the stellar mass within 250 parsecs as well, or the total stellar mass?
For, when we compare with SFR, this is the total. You mean the stellar mass? Stellar mass is the total, not only the one within
not the aperture mass. Okay.
Yeah, not the aperture ones. This is the total stellar mass.
Okay. Matt Hayes asks, if the galactic winds are important, have you made any measurements using absorption lines, such as with velocities or covering fractions?
This current analysis is focusing on the photometric aspects, but so we haven't directly checked the absorption properties yet. But yeah, that would be definitely a interesting point.
Okay. Yuki Isobe asks, could you please remind me the motivation you distinguish Greenpeace and Lyman break analogues? What are the differences between these?
The basic difference between the two classes of these local analogues is the different sample selection technique, where Greenpeace galaxies are selected based on their strong O3 emission line imprinted in their R-band image. So they are emission line selected samples, whereas Lyman break galaxy analogues are UV continuum selected samples. So although they are both local starburst galaxies, their sample selection is basically different, and which causes some differences in their physical properties as well.
Okay. Tom Toons asks, do you think the dependence on M star could be related to metallicity rather than halo escape velocity?
Yeah, that's a great point, and yeah, we also considered M star could be reflecting low metallicity effect, but when we consider the dynamic range of this specific star formation intensity, for example, here from minus 10 to the minus 9 up to 10 to the minus 6.5, which is wider than just the gas phase metallicity range. So we are more tempted to interpret this whole effect is likely caused by the linear M star effect, which is a gravitational potential. But yeah, we also know there are some there could be some gas phase metallicity effect, but that is only within a depth, one depth. Yeah.
Right. So there's unfortunately there's a few more questions, but I think we should move on in the interest of time. So thank you, Keunho, and please do check the Slack when you get a chance, and you can see all the other questions that are there.
Yes.
So thank you very much again, and we'll move on to the next talk, which is by Simone Gazagnes, who will tell us about the escape of Lyman alpha and ionizing photons in Lyman continuum emitters. So there you go. And
yeah.
there you are.
Well, timer. Well, first, I would like, of course, to thank the organizer for this very nice opportunity to present our work during this complicated time. So my name is Simon Gazagnes. I'm a third-year PhD student in Groningen, so in the Netherlands. I'm going to talk today about work that I've been conducting for some years now with this very nice team of people, where we try to understand the origin of the escape of Lyman alpha and also ionizing photons in local Lyman continuum emitters. So the context of this work is that typically, if we want to understand whether and how star-forming galaxies have contributed to the ionization, we need to constrain this quantity, which is the escape fraction of the ionizing photons that escape from this galaxy in the intergalactic medium of the universe. But in order to do so, it's a very complicated task because we need to directly observe the wavelength range that are below 912 angstrom in order to have a direct constraint on the escape fraction of these ionizing photons. And at high redshift, it's highly infeasible because of the IGM opacity mainly. So we need to find these indirect proxies to estimate the escape fraction of the ionizing photons in high redshift observations. And how do we do so if we don't have enough observation? Well, we can use these analogues. So basically, over the past decades, we had now 15 direct detections at redshift less than 0.5 with escape fraction between 1 and 73%. And these analogues are very interesting because we have this spectroscopic observation with costs between 800 and approximately 1300 angstrom, on which we can do a lot of interesting things. The first one is obviously that since we have direct observation of the wavelength range below the Lyman break, we can have a direct constraint on the escape fraction of the ionizing photons. But now if we look a bit redder, we have this H1 absorption lines, the Lyman series, that can tell us a lot of information about what kind of neutral gas properties do we have in these galaxies. And again, if I push it a bit redder, we have this Lyman alpha emission profile that looks like this double or triple peak in most of these local galaxies. And Lyman alpha is this resonant transition, which is very sensible to the kinematics and general distribution of the H1 gas in the galaxy. And similarly, it tells you a lot about these natural gas properties. So if we combine this three wavelength range, basically what we can do, among other things, obviously, is first investigate what kind of natural gas properties are favoring the Lyman continuum leakage. But also a very important point is to use these additional properties that we extract on the spectroscopic observation, find some way to indirectly estimate the escape fraction of ionizing photons and compare it to the observed escape fraction that we derive on the observing flux. Ionizing flux. And that's basically what I've been doing and being interested in for a couple of years now. And it started in 2018. So basically, we took a sample of leakers with escape fraction lower than 13%. And we found out that all the leakers in our sample had these saturated H1 absorption lines, but not fully covered, so that the Corin fraction of the H1 dense gas is not unity, which suggests that in this galaxy, you have a part of the light that escaped through some path with few or no H1 residuals, basically. And additionally, we found out that in the dense regions of the ISM of this galaxy, we have a column density higher than 10 to the power 18. And this column density suggests to you that no ionizing photons can escape through these dense regions. And from this combination of two results, we actually supported that these leakers have this kind of ISM configuration, what we call ionization bounded or pick and fence model. Well, we have an optically thick H1 shell that is surrounding the Becker star, but we have some holes in this shell so that the ionizing photons can escape through it. And this outcome there was also supported by a second study, a companion paper from John Kisholm, when John Kisholm shows that if you use this equation, so 1 minus the Corin fraction of the H1 gas, which is basically what goes through these low column density channels, and you combine it with the dust attenuation that should impact the ionizing photons, which is this. So you can predict the escape fraction, which is this quantity here. And the prediction is quite accurately reproducing the observed escape fraction in these galaxies. And this is a very powerful result, especially because even if the Coring fraction of H1 is also difficult, hardly measurable at high redshift, we found out in 2018 paper that the Coring fraction of the silicium-2, for example, could be a very good probe to the Coring fraction of the H1 gas, as you can see by this strong correlation. And the idea that this Coring fraction is more likely to be measured at high redshift observation, and I will come back to this. So based on this equation, using the Coring fraction of silicium-2, we could already infer some kind of estimate of what is the escape fraction of Lyman continuum in this high redshift galaxy. So this is where we were in 2018. And recently, a few months ago, we published this additional paper. Basically, what we did is we took a larger sample of low redshift flickers, and we analyzed in the same paper the Lyman alpha properties, the H1 properties, and combined it to the measured escape fraction of the Lyman continuum photons. And what we wanted to do first, and there is a lot of very interesting results about this that unfortunately I have no time to talk about it, is to connect how the Lyman alpha properties relate to the ISM porosity, to the presence of a low Coring fraction of H1. So since I have no time to talk about it, I will put some slides or likely a poster on this channel or Slack. So if you are interested by this result, please check this channel tomorrow, probably I will put it. What I will focus it is that in this paper, as I said, we use a larger sample of flickers. Basically, we include 6 additional low redshift flickers, and 3 of them have this very large escape fraction of 36, 48, and 73%. Which is very useful to assess the robustness of this indirect prediction of the escape fraction of ionizing photons that is using the Coring fraction of H1. And this is what I will focus now. And basically, how does it look like? It looks like this. On the y-axis, we have again this predicted escape fraction of ionizing photons, which is computed with this equation. On the x-axis, we have the observed escape fraction of ionizing photons measured on the ionizing flux. And the stars are the new liquors that are added in this recent paper. And what we found out is like for liquors, again, that have moderate escape fraction of ionizing photons, these predicted values are reproducing quite well the observed escape fraction within 3 sigma. But now if we look at the largest liquors, we found out that the predicted escape fraction are underestimating by more than 3 sigma the observed escape fraction for these galaxies. And what we suggest in the paper is that actually in these specific 3 large liquors, we don't have enough H1 in the dense regions of the ISM, such that if you consider only what goes through the low column density channels, you underestimate the total observed escape fraction of the ionizing photons. And that is what is summarized by these toy models that we think are the accurate models for the Lyman continuum escape in this galaxy. And the main difference in the large liquors is that we think that, for example, these high density clouds that in the low liquors are too thick to allow the ionizing photons to escape. In that case, they don't have enough H1 such that a significant fraction of Lyman continuum photons can also escape through this path. So yeah, so if I come back to the main idea of this talk is to find a way to estimate the escape fraction at high redshifts. And what this result shows also is that even if you underestimate the escape fraction of the ionizing photons for large liquors, you still have quite a good constraint, like a lower limit on what is the observed escape fraction of the ionizing photons in these galaxies. And additionally, it seems that you can disentangle from liquors that have a low escape fraction of ionizing photons or liquors that have a higher escape fraction of ionizing photons, which is ultimately what we want for high redshift observations. And as I said previously, that we found out that the Coring fraction of low ionization metals like silicium-2 can be a good probe of the Coring fraction of the H1 gas. And that's something that we should be able to measure on high redshift observation with JWST especially. So the idea is from this Coring fraction of the silicium-2 to infer the Coring fraction of the H1 gas and to use it in this equation to find the first lower limit on what is the contribution of this star-forming galaxy during the epoch of reionization. So if I wrap up and summarize the three ideas that I would like you to remember is that from these studies, we found that the ISM porosity, so the presence of a low current fraction of H1, is strongly what enables the escape of both Lyman alpha. I didn't talk about it, but obviously the escape of Lyman continuum photons in this galaxy. But additionally, in the large leakers, we must have some additional escape mechanism because we only recover a lower limit to the total escape fraction that we observe. And the most importantly is that the core infraction of these metal lines combined with the dust attenuation at 912 angstrom should provide the good lower limit to estimate the contribution of this galaxy during the reionization. And I will stop here. Thank you.
Thank you very much, Simone. So yes, very clever method. So we have some questions on the Slack. So we'll try to get through as many as we can here. The first one from Harold Melema. NES, I assume that your F escape is, as a function of Lyman continuum, is the value along the line of sight, whereas the value interesting for reionization is the 4 pi escape fraction. So in all directions, in view of your model, how can measurements of the FS along the line of sight help us establish the escape fraction in all directions?
Yeah, it's a good question. So yeah, obviously the escape fraction that we are talking about here is along the line of sight. Now, the thing is that if we have a picket fence model as this leaker suggests, well, it's likely very heterogeneous, this escape fraction, that it might change from line of sight to, depending on the line of sight that you observe. So how from this result estimate the global escape fraction that is average over 4 pi? This, I'm not sure I can answer this question.
Okay.
I mean, I will think about it.
Yeah, something to think about. So Matt Hayes asks, for these high F escape cases, what estimate would you get from the Lyman alpha profile? And can you do something like get the residual H1 fraction from the ionized H2 gas?
Sorry, can you repeat?
So he asks, what estimate would you get for the F escape from the Lyman alpha profile? And can you do something like get the residual H1 fraction, I guess this is the covering fraction, using the ionized H2 gas?
So I don't know what kind of estimate we get from the peak separation of the Lyman alpha profiles, for example. I know that these 3 leakers have one of the smallest Lyman alpha peak separation. And the second part of the question was, how do we estimate? I'm sorry.
The H1 fractions, H1 covering fractions.
From the Lyman alpha profile?
Sorry. The question is, can you do something like get the residual H1 fraction in the ionized H2 gas?
Yeah, if the peak separation of Lyman alpha probes what is in these low column density channels, then I think we should be able to get an estimate of what is H1 residuals in these channels.
Okay. I think we'll probably take one more here, maybe 2. Rohan Naidu asks, what are your best guesses for the additional mechanisms driving the F escape in the most extreme leakers?
Well, it's was I suggested here that, so in the low escape fraction case, we are able to recover the total escape fraction, total observed escape fraction, if we consider only what goes through these low column density channels. But for the large escape fraction, we have this evidence. So one of the largest leakers, for example, we do not detect any H1 absorption gas, which suggests that even in the densest regions of the ISM, we have very few H1 residuals. While for the 2 other large leakers, we have also evidence that we have some dense gas, but this dense gas is also at column density that are too low to absorb all the radiation that pass through these clouds. I hope it answers the questions.
Right. They can extend below the Lyman limit. Okay, last question. Danielle Berg asks, and there are more questions, so you have to go on the Slack to see them. Nice. Do you see any trend between the Lyman alpha kinematics and the covering fraction?
Yeah, it's a good point. So we see So I don't have this picture. So if we superpose, for example, the Lyman series line to the Lyman alpha profile, we see typically that the peak in galaxy with the lowest scoring traction of H1, the position, the velocity of the blue peaks correspond basically to the velocity of the H1 absorption lines. So suggesting that these blue photons escape directly through these low column density channels because it's also the velocity where the H1 gas should be the most absorbing. So we indeed see that the velocity where we measure the covering traction correspond to this velocity where we see the blue peak of Lyman alpha. So there should be this is a strong insight that tells us that these photons escape through these low column density channels.
Okay. Thanks. There are many more questions, so please check the Slack when you get a chance.
Thanks.
And we'll move on to the last talk of the session. So Romain Meyer is going to speak. So yeah, he's on. So please share your screen.
Yeah.
And there
Right.
you go.
There you go.
Yep.
Okay. Thank you very much. I'd like to thank the organizer for giving me the opportunity to talk. It's been very nice yesterday and today, and I'm sure it will continue to be so. So I'm a finishing PhD student at UCL, and I want to talk to you today about work I did during my PhD on escape fractions of redshift 6 galaxies. So if I'm talking about escape fractions of redshift 6 galaxies, Lyman continuum escape fractions, you're probably thinking about this. So here you have on the plot the IgM neutral fraction history as a function of redshift. And to match this IgM neutral fraction history, you would go usually with an analytical model. You would compute what we call the ionizing photon budget. And so simply you would say, okay, I know the number density of the luminosity density, sorry, of the UV luminous sources. I know their ionizing efficiencies from the UVLF, from measurements at redshift 4 to 5. And then basically you can fit for the escape fractions. And so in doing so, you would say, okay, galaxies, if they did reionize the universe, they would have needed an average escape fraction of 10, 20%. The problem when you do this, it's an average statement. You're not actually seeing galaxies reionize the universe. You just say for this to be possible, they should have 10%, 20% escape fraction. And also it's completely degenerate with any luminosity dependence. So for example, in the paper from Rohan Naidu, he showed that you can basically fit the same data with pretty much a model with bright sources ionizing the universe with high escape fractions, or a lot of faint sources with low escape fractions. And so today I want to take you through two measurements, which are actually measurements of escape fraction at redshift 6. So the first one is the galaxy IgM cross correlation. So we will see how galaxies can actually impact gas that we probe with the background quasars and how we can infer escape fractions from that. And then individual measurements from double peak Lyman alpha. We talked a lot already today, and how we can actually bring all of this together. So starting with the galaxy IgM cross correlation, we all think of reionization as these bubbles, this Swiss cheese topology, and we all like to think that galaxies actually power these bubbles. And so if you look at a distant quasar greater than redshift 6, you have the Lyman alpha forest, or what remains of it at this redshift, and you have opaque troughs and transmission spikes. And so around transmission spikes, you're actually tracing ionized gas. And so there should be galaxies ionizing this gas. So the question is, can we actually measure that correlation between galaxies and Lyman alpha transmission? And how can we infer escape fraction from this? And so we've written a paper series, and I want to go over the latest result from the third paper. So to do this, we take quasars. So here you have the 8 Lyman alpha forest of the quasars, about redshift 6, so 5.8 to 6.5. And so we've doing a Lyman break, Lyman alpha emitter survey with MUSE or DMOS. And so MUSE is in blue, DMOS is in orange, and you can see all the galaxies that we detect. So we detect the Lyman alpha emission in the field of that quasar, and the distance from the x-axis is just the distance. And you can see that, for example, in 1030, that's your poster child. You have a lot of transmission spikes, and next to the transmission spikes, you have a lot of galaxies. So that galaxies do reionization, do transmission spikes. But if you look at 2329, it's a completely different story. You cannot do this one-on-one association. So you need some more statistics, and that's why we do the cross-correlation function of galaxies with Lyman alpha transmission spikes. So we identify the spikes with Gaussian match filter, and then we do this 3D cross correlation, and we find that around LAEs or LBG, you have an excess of transmission spikes. And that's great because you can see, okay, I target galaxies that are probably traces of other densities, and I see more ionized gas. So reionization actually happening, and you can observe it. But we want escape fraction, right? So let's go further on how we model this. So I don't have time, and I encourage you to have a look at the papers if you're interested. But basically, if you sit down and do the calculation, a single LBG or LAE cannot ionize the gas enough so that you have a transmission spike in the Lyman alpha forest of the quasar. So you need to take into account that there are many other faint galaxies clustered around what we call the bright traces. And so we have a HOD modeling, and we compute how many galaxies you expect to be clustered around these objects. And so in doing so, you need to fix what is the minimum UV luminosity of contributors. So that's the first parameter of the model. You fix the luminosity average escape fraction, of course, and the host halo mass, because the more massive your tracer, the more galaxy will be clusters, and so the signal is stronger. And this one is fixed, actually, because we more or less know the host halo mass of LA and LBGs, but the two others are actually the parameters we can fit for. So before I show the results, well, there's the title already, but I just want to emphasize we constrain the luminosity weighted average. So I will treat it as the average escape fraction of all galaxies, but actually if you have some luminosity dependence that you prefer, you can fold it into this equation and compare to our observations. So here is what we find. So what you see is in blue and orange, so these are the posterior. So this is the constraint on the luminosity average escape fraction. And these are as a function of the minimum UV luminosity of the contributors to reionization. And you can see we have this banana basically constraint, which is actually normal. Even if there is a dependence on the signal, the slope changes a bit as a function of the minimum UV luminosity. You're mainly constraining the total ionizing output of all the galaxies around your LAEs or LBGs. So you can either have bright galaxies only contributing with very high escape fractions, or faint galaxies, all the galaxies contributing with an average escape fraction of 10–20%, and this agrees very well with the neutral fraction history measurement that you can see here in black. In any case, whatever you choose, they must have greater than 5 or 10% at 2 sigma escape fraction. And so I'm not talking about the LAEs or the LBGs. Remember, I'm talking about basically every galaxy is clustered around our traces. So how do we distinguish between the two cases, faint galaxies dominating, bright galaxies dominating? Well, remember here, the constraint is that if only bright objects were contributing to reionization, they should have on average about 90–100% escape fraction. So let's go and measure the escape fraction in these bright objects and see if they have 100% escape fraction or not. And then we can tell if the faint or bright objects are contributing the most. So how do we do that? Well, hopefully people luckily covered this before me. So we have a lot of Lyman continuum emitters and Greenpeas at low redshift that have double peak Lyman alpha. And so we know there is a tight correlation between the peak separation of Lyman alpha and the Lyman continuum escape fraction. So you could go at high redshift and measure this. Unfortunately, the IGN damping wing usually absorbs and kills the blue peak. So these objects are very rare, and we only have 3 so far with escape fraction from 1 to 29%. Well, actually, we have 4 because we have a new one that I'd like to show you. So it's called A370PZ1. So it's found in the parallel field of Abel 370, and it has a strong drop in the Z band, hence the unimaginative name. So it has a very strong break. It has also a 3.6 excess, and this is very exciting because it indicates it's a high O3 emitter, and we've heard many talks on this today. And so photo Z of redshift 8, and we have this very nice double peak that we have seen in the spectra. So this is X shooter, 6 hours. The peak separation is actually way too large compared to low redshift doublets, so it cannot be this. And we have no additional lines, so we're pretty confident. This is double peak Lyman alpha at 6.8, and the velocity separation is 100. So with a velocity of 100, velocity separation of 100, what is the escape fraction? Well, the problem is that the low redshift relation from Isotov et al. Basically overshoots in that regime, so we can only have a strong lower limit constraint using that. And the constraint is very strong. It's greater than 59% at 2 sigma. So, we have an object that is basically near unity in terms of escape fraction of Lyman continuum photons in the reionization era, redshift 6.8, which is quite cool. You can also, not using the empirical relation, you can compare to static shell models that they've been developed for years. So here you can see 3 different models. And if you take, for example, the orange or the blue ones, depending on if you want to fit better the peak or the trough, you get an escape fraction of 95%. So I can now go back to the constraint I showed you before. And I can say, well, we've looked, okay, 4 objects, but we've looked at MUV minus 21 objects in the reionization era, and their escape fraction is about 30%, plus minus 30% on average. And so this is inconsistent to sigma with the constraint that we have from the 2-point cross-correlation function. Therefore, the combination of these 2 probes and also the metal IgM cross-correlation that is shown here, second paper in the series, suggests that we really have reionization that is dominated by the faint galaxies. And so I hope I have convinced you that these probes can be interweaved and combined together to give nice constraint on reionization. And hopefully in the future, both on the double peaked and on the cross-correlation, we will have more data coming from JWST+ALMA and ground-based surveys. And I hope also we will have more methods to measure directly the escape fractions at redshift 6, perhaps with the low ionization absorption lines with the LT. Thank you very much.
All right, thank you, Romain, for that excellent talk. Yeah, do we have some questions? Yes. So we'll start with Harley Katz, who asks, the faint galaxies around the massive galaxies can be quenched due to radiation feedback, of course. Do you think that there will be a bias in your F-escape measurements from cross-correlations by preferentially selecting environments around Lyman break galaxies?
Yes, so that's an excellent question. Yes, obviously the issue is when you do this, if you take LBGs, especially LBGs, because you're pre-selecting them based on the break, but then you don't look at any break galaxy, you look at them, the ones that you can confirm the redshift of. So you're looking at the ones that are in highly ionized environments, and so perhaps you're selecting indeed the environments where you have the most efficient leakers, meaning the constraint that we have target a subpopulation that is the most efficient leakers in the universe. So I think that's why we have to vary the probes. So LAs are perhaps not the best, but metal absorbers, and then with James Webb, we'll target O3 emitters, O2 emitters, or H alpha. And so hopefully in that way, we can avoid the biases due to having Lyman alpha as a spectroscopic redshift.
Okay. So Rohan Naidu asks, what is the blue to red peak ratio in your double peaked emitter? From low Z sources, the typical blue to red peak ratio seems to be about 0.3. Could this be a merger?
Right. So the blue to red peak ratio is about 60 or 70%, I think. So, well, we cannot exclude a merger. We can never exclude a merger. However, I can say from the 2D, there is no offset between the 2 peak, at least not that we can measure. So of course, this would be very interesting to look at with an IFU. I can also say that on the HST data, it looks very round. It does not look perturbed or elongated. So as far as we can tell, it's not a merger. But of course, the best would be to have an IFU there, of course.
Okay, and maybe take one more question. Fahad Nasir asks, due to fluctuations in the Lyman alpha 4 sightline, the transmission spikes might not always correspond to overdensity. It could be a hot ionized cosmic void. You consider this when calculating your cross correlation?
So we have a temperature density relation in the model. I'm not sure if that addresses this completely, but you're right. It's not only over density. There, we've considered smaller mean-free path. We've done a self-consistent mean-free path as well, depending on the ionization and the density. I think ultimately the analytical model is good because it gives you a nice estimate of the escape fraction. But ultimately, you really want a simulation, and I really hope we will see from simulators that kind of measurements. I know it's difficult. You need long skewers, and you need to model the galaxies. But hopefully, in the end, that's what we will have.
All right, maybe let's take one more question here from Daniel Scher. Great talk. Have you been able to detect any other emission lines also to have an independent redshift for the Lyman alpha line profile interpretation?
No, unfortunately, we don't. We have no additional emission line, so that's very sad. But the photo Z is very robust. The break is about 4 magnitude. So even with the Balmer break, it would be difficult. I mean, you can't fit it with a low Z solution, and if it was a low Z doublet, then you would have, or even not a measure of low Z lines, you would have other lines, H alpha or O3 or H beta. So it's really, I mean, it's really difficult to imagine this is low redshift. But of course, the next step is having probably ALMA and then James Webb on this.
Excellent. Okay, great. Thank you very much, Romain. And that has concluded our session. Steve, do you have anything to add before we adjourn for the day?
I think we are good. I'm one of the Steves, at least. I think we're good. Thanks, everybody, for such wonderful talks. I do think one reminder is that we do have 4 sessions tomorrow. I'm going to double check so I don't get the times wrong. But session 3A is tomorrow at 8 o'clock UT, followed by session 3B at 10 o'clock. And then session 4A and 4B will be at the times we've been doing today and yesterday.
Yeah, I was just going to add that reminder. And I was also just going to mention very quickly, by request, we've now added the functionality to ask anonymous questions. Although unfortunately you can't ask them in exactly the same way as we've been asking them before. If you just look on the Slack general channel, there's an explanation there. And hopefully see lots of people early tomorrow. I'll be interested to see how many people we have in the morning. Sorry, morning in the UK.
Middle of the night in Texas. Yeah, okay, so have a good evening or morning or rest of your day, and we will catch up again tomorrow.